Chapter 8 Differential Equations Subtopic 5.1 Part 2 and 3 Differential Equations where dy dt equals to ky plus m. This is our learning objectives. Differential equations where dy dt equals to ky plus m, where k and m are constants, has exponential form of solution y equals to ab to the power of kt plus c, where a, b, c are constants, a and b being positive. Example number 1. In a salt mixing problem, the amount of salt in the tank at any time t minutes is given by differential equation ds dt equals to 1 minus 0.04 s and initial condition s0 equals to 20. Part A. Assuming that s equals to ae to the power of kt plus c, find ds dt, and hence find k and c. Part B. Use the initial condition to find a. C. Explain what happens when t gets large. D. How long would it take for the salt to reach 22 kg? E. Sketch the salt content of the tank against T. This is our solutions. Part A. S equals to AE to the power of KT plus C, meaning S minus C equals to AE to the power of KT. Differentiate S with time, ds dt equals to ak e to the power of kt. So when we rearrange this expression, we can get ks minus kc equals to 1 minus 0.04 s. By comparing, we can get k equals to negative 0.04 and the value of c is 25. For part B, since S0 equals to 20, so we will get A equals to negative 5. Part C, as t gets large, e to the power of negative 0.04 t will go near to 0. That means the amount of salt in the tank approaches 25 kg. Part D, when s equals to 22, we will get the equation negative 5 e to the power of negative 0.04 t plus 25 equals to 22. Solving this equation, we can get t approximately 12.77 minutes. As for part E, the graph, please refer to textbook, page 274. Now, let's look at example number 2. Example number 2 is about Newton's law of cooling. Newton's law of cooling is the rate at which an object changes temperature is proportional to the difference between its temperature and that of the surrounding medium. That is, d capital T over dt equals to K times T minus Tm, where capital T is the temperature of the object and Tm is the temperature of the surrounding medium. K is a negative constant called the cooling coefficient. Here, this is the question. Part A. A copper has a cooling coefficient of negative 0.19 and a copper rod, which was out in the sun, cools from 65 degrees Celsius to a room temperature of 15 degrees Celsius. Show by differentiation that capital T, the temperature, equals to 15 plus 50 e to the power of negative 0.19 t. Satisfy the differential equation d capital T over dt equals to negative 0.19 times t minus 15. T0 equals to 65 and t is the time in minutes. Part B. How long would it take for the temperature to reach 20 degrees Celsius? This is the solution for part A. So when we differentiate capital T, we will get dt over dt equals to negative 0.19 times 50 e to the power of negative 0.19 t. So from the initial equation that we have, t equals to 15 plus 50 e to the power of negative 0.19 t, we get 50 e to the power of negative 0.19 t equals to t minus 15. So use this information and we get the expression as required. Here. This is the solution for part B. So when temperature reached to 20 degrees Celsius, we will get the equation 20 equals to 15 plus 50 e to the power of negative 0.19 t. Solving this equation will give us t approximately 12.12 minutes. Capacitor resistor circuits. For capacitor resistor circuit, the differential equation involved is dq over dt times R plus q over C equals to E, where R the resistance, C the capacitance, and E the voltage are fixed. Or when we rearrange this equation, we can get dq over dt equals to E over R minus 1 over CR times Q, where E over R and 1 over CR are constants. The exponential solution has the form Q equals to A e to the power of kt plus a C. For this type of problem, please read example number 3 on page 276 in our textbook. And your homework is exercise 8.2 on page 275 to 276.